Welcome to The Explainer. So, today we're going to look at something you probably interact with every single day, without ever stopping to think about how you actually learn to do it. We're talking about numbers, but we aren't looking at high-level data models or complex algorithms here. Instead, we're going to uncover the deeply surprising cognitive science hidden right inside a Year 1 math textbook. It turns out, the way we first learned to process numbers is actually a fascinating blueprint for how our brains handle complex information for the rest of our lives.
So how do we actually learn to understand numbers? Seriously, pose this question to yourself right now. For the next few minutes, I need you to completely forget everything you know as a highly capable adult. Just wipe the slate clean. I want you to view this problem entirely through a child's eyes. You know, when a number is just a meaningless squiggle on a page and a pile of blocks is just a pile of blocks. How does the brain actually start to build the structural logic of mathematics?
Okay, let's dive into this. Section 1. Seeing numbers without counting. Our very first cognitive milestone isn't really what you might expect. I mean, we usually think of math as counting, right? 1, 2, 3, 4. But look at this exact instruction straight from the source material. Do not count. What numbers can you see? This is literally the ultimate paradox of early math. The very first step to counting effectively is actually learning how not to count. Instead of individually pointing at items one by one, the brain has to learn to instantly recognize quantity as a whole visual block. Check out how the learning material pairs these rectangular grids, what educators call 10 frames, with images of hand gestures. You've got an empty 10 frame, then one red dot, then two, progressing all the way up to 5. And right below them, hands holding up the corresponding number of fingers. By grouping these dots into organized frames and pairing them with super familiar finger shapes, the textbook is actively training the child's brain to just completely bypass manual counting. When you see 3 dots in a row or 3 fingers held up, you don't calculate 1 plus 1 plus 1. You just instantly recognize the pattern of 3. This visual shortcut is an absolutely critical foundation for all future data processing.
Moving right along to Section 2, many ways to show numbers.
Once the brain can visually recognize a quantity, the textbook immediately forces a brand new challenge, which is building immense cognitive flexibility. And this brilliantly illustrates that shift. Just look at all the wildly different ways a child is asked to understand the number 6. It's definitely not just a digit. 6 is a full hand plus 1 finger. It's 2 rows of 3 red dots on a dice. It's a pyramid of stacked yellow cubes. It's a symbol written on a runner's racing bib. And it's a specific pattern of red counters inside a 10 frame. The brain is learning that this invisible, totally abstract idea called 6 can be firmly grounded in completely different real-world physical and visual representations. It doesn't matter what form the data takes, right? The underlying value stays exactly the same. Which leads us to this incredibly powerful little instruction. Move the cubes around. The number stays the same. Now, as adults, this seems painfully obvious. But for a developing brain, this teaches the conservation of quantity. It is a massive, monumental developmental leap. It proves that spatial arrangement, whether those cubes are in a really tall tower, spread out in a messy line, or grouped in a circle, does absolutely nothing to change the total amount. The value is completely independent of the visual layout.
All right, Section 3, patterns, memory, and play.
So we have visual recognition, and we have cognitive flexibility. But static concepts just aren't enough. We need to transition into how these static visual ideas get turned into active, interactive exercises that push the limits of memory and spatial reasoning. I want you to mentally engage with this matching exercise for a second. We're looking at numbers 6 through 10. On one side, we have complex, asymmetric hand shapes, like a full hand of 5 plus 3 fingers on the other hand to make 8. On the other side, we have the highly structured, symmetrical rows of a 10 frame. Drawing a line between these two requires the child to literally translate one visual language into another. They're building crucial mental bridges, confirming that 8 messy fingers perfectly equals 8 neatly organized dots. Then the book takes these concepts and weaponizes them into a game. Look at this sequence. Make a pattern with cubes, hide it behind a book, show it quickly, and ask your partner how many you used. Now pay close attention to that show it quickly part. Why quickly? Because it explicitly forces the child to use that instant visual recognition skill we talked about earlier. If you show it quickly, your partner simply doesn't have time to count the cubes one by one. They have to capture the whole image in their memory and recognize the pattern instantly. It completely turns a static counting exercise into a high-speed, dynamic mental drill.
And that brings us up to Section 4, building the number sequence.
Here we arrive at the final thematic pillar. This is where all those isolated recognition skills, the memory games, and the spatial reasoning are finally strung together into sequence logic. 20. This is the massive numerical goal of this entire early learning unit. Getting to 20 means you don't just know individual numbers anymore. You understand exactly how they relate to one another in a continuous, predictable chain.
Now, what's really interesting here is how the culminating math quiz visualizes the absolute ultimate test of everything the child has just absorbed. This isn't just a simple test of memory. It's actually a multi-layered cognitive assessment, beautifully disguised as a colorful activity. Let's break down exactly what this is asking a child to do, because it tests several entirely different modes of learning all at the same time. First, they have to count scattered red cubes. That's visual tracking and spatial organization. Then, they're asked to make a physical tower of 20 cubes, bringing in physical building and tactile feedback. Next, identifying missing numbers in a sequence, like figuring out that 5 belongs right between 4 and 6, which tests pure logical sequencing. And finally, they are instructed to trace each number with their finger while saying it out loud. That literally locks in the concept using tactile motor skills combined with vocal repetition. It is an incredibly comprehensive, full-brain workout that makes sure the concept of numbers is completely hardwired into multiple neural pathways.
So the crucial takeaway here is this. The math itself may be simple, but the mental architecture being built is profoundly complex, which leaves us with a pretty fascinating thought to consider. How do these exact same visual, tactile, and sequential building blocks continue to shape the way you interact with numbers and data today? When you instantly read a bar chart, estimate a budget, or effortlessly spot a missing value in a giant spreadsheet, you are standing directly on the foundation of these playful, brilliantly designed childhood exercises. It really makes you appreciate the hidden mechanics of learning, doesn't it? Thank you so much for joining me for this explainer, and keep exploring those patterns hidden right in plain sight.